Okay, welcome to the new module. This is basically about chemical reactions and energy. So we're going to go over some basic principles first of energy. The first goal is to recognize and use the language of thermodynamics. Thermo meaning heat, dynamics meaning changes, so heat changes. The language of thermodynamics, the system and its surroundings, exothermic and endothermic reactions. We want to describe the nature of heat as heat transfers as energy and understand the signs, conventions of thermodynamics. Okay. So we'll take a look here at energy and molecules. There's basically two types of energy: kinetic energy, which is motion energy, and that's thermal or heat energy. And that's basically what we're talking about in this particular section. Although we also include some talk about potential energy, which is the energy found in bonds and intermolecular forces, forces between molecules. So, using energy to study chemical reactions, basically we use these three ideas. The law of the conservation of energy, which says that energy cannot be created or destroyed, but it can be converted. You can take kinetic energy and turn it into another type of kinetic energy. Potential energy into another type of potential energy. Kinetic into potential and potential into kinetic. So we can convert it, but we can't change the amount. We want to be able to use sign to indicate the direction of heat flow. So for heat, we use the symbol Q, and we find that it's very useful to indicate whether or not heat is flowing into something or flowing out of something. And so we want to be able to use sign to indicate that, since it's either going in or out, so plus or minus. And then thermal equilibrium introduces the idea that basically heat flows from hot objects to cold objects. So if you have a hot object designated by my hand being kind of high and a cold object by my hand being low, when energy flows into the cold object, it gets warmer. But what happens to the hot object? It gets colder. And eventually the heat flow stops because this does not happen. The cold object does not get hotter than the hot one, and the hot get colder than the cold. They reach thermal equilibrium, which means they're the same temp. And so we know that energy flows from the hot into the cold, because if we're the other way around, if energy flowed into the hot would get hotter and the cold would get colder. And we don't see this. So we know that energy flows from the hot to the cold. Until when? Until they reach the same temp. So let's take a look at this in a little more detail. So objects in thermal contact, they share heat. And these could be the system and the surroundings, if you will. And we refer to this as the system and the surroundings. And usually the system and the surroundings, we try to make it something simple to work with, and we ignore a lot of things. So we make a lot of assumptions. So you might have a glass of ice water, and you say that the system is the ice and the water is the surroundings, and you ignore the glass. You say, well, the glass really isn't absorbing any heat or adding any heat. And that may or may not be the case, because if you are using a glass, that's not the case. But if you're using a styrofoam cup, it works pretty darn well. Okay, you could have the ice being the surroundings and the water being the system. So basically what you define as the system and what you define as the surroundings depends on your frame of reference. Your system could be a person who jumps into Humboldt Bay. So what's going to happen with these two things? They'll come to thermal equilibrium eventually. And that means that the person will be very cold because they can't warm up the Humboldt Bay. It could be a chemical reaction. A lot of times, and this is the hard one for people to understand, the system is something that's not tangible, but rather it's an event. So a chemical reaction can produce heat, and that heat can warm up the solvent. Okay? All right. So that's system and the surroundings. Here's the direction of heat flow. Here we make some terms that you need to understand. Endothermic means heat flow into, and Q, which stands for heat, is positive. So when you are absorbing heat, that's called an endothermic process. On the other hand, if you give off heat, heat flow is leaving, we say Q is negative, you're losing heat. So when you stand around and you're radiating heat, you're losing heat. Okay. When you drink that hot cocoa, though, that's adding heat too. You're absorbing heat. So when you drink the hot cocoa, endothermic. When you stand around and just radiate heat, that's exothermic. Now, let's take a look here just at A. So here's the system and here's the surroundings. This is a common cartoon drawn where the surroundings, of course, surround the system. And look at event A here where you have Q of A, the heat for event A. So you can see that heat is leaving the surroundings and going into the system. So here, since energy is being absorbed by the system, we say that this event is endothermic for the system, and it's exothermic for the surroundings. So endo, because we're adding heat to the system, and exo, because we're losing heat from the surroundings. Now, the interesting thing here is that if the amount of heat being absorbed by the system is plus 5 kcals, that means that the surrounding, due to the law of the conservation of energy, has to be losing specifically minus 5 calories of energy. Now, this endothermic and exothermic can be applied to the system or the surroundings. So let's look at situation B, where energy is leaving the system and going into the surroundings. So for the system, this is considered to be exothermic, energy leaving. I like to use the word exiting for exothermic. And endothermic for the surroundings. So if Q of B is 3 calories going into the surroundings, then Q of the system has to be -3, losing 3 calories. Let's look at thermal equilibrium and the law of the conservation of energy. So basically, it can be summarized this way, and this is going to be found in a later section. The sum of the Qs for those things that are in thermal contact is equal to 0. And the reason this works is because some energy is entering, some is leaving, but the amount leaving and the amount entering must always equal. So that means that the overall change is 0. So when you sum all of these events, the sum is 0. So if we take a look at a very simple thing where we have one system, one surrounding, the Q of the system plus the Q of the surrounding is 0. And the Q of the system is equal to negative Q of the surrounding. We could actually have this Q1 plus Q2 plus Q3 plus ... is equal to 0. So this is a case where you have many different things that you're studying, if you will, many different systems and the surrounding. So this is another example where it shows you that the amount of energy flowing into the system is plus 10 calories, then the amount leaving the surroundings has to be minus 10. How do we know it's energy leaving the surroundings? Because it's a negative value. Positive means it's going in, absorbed. Negative means it's leaving. Okay, so let's take a look at this right here. Some basic principles. First, let's define the terms system and the surroundings. So what are we going to say for that? Well, system is the object or event being studied. And the surroundings are those things in thermal contact. With the system. Okay. So what does it mean to say that a system and a surroundings are at thermal equilibrium? Eventually, the system and the surroundings reach the same temp. i.e., reach thermal equilibrium. Okay, so there we go. Let's take a look at this next one. Identify whether the following processes are exothermic or endothermic, and is the sign positive or negative. So let's take a look at this first one. Combustion of methane. So methane, when you combust it, This is not a balanced reaction, but this is what you get. And we can probably balance it pretty quickly because one carbon, 4 hydrogens, now 4 hydrogens, 4 oxygens, now 4 oxygens. Okay, so when you combust this methane, you get heat. Heat is actually a product. So here, when you produce heat, that means that heat is released. Same thing as produced is released. And so here, that would be an exothermic reaction. And because it's exothermic, it's negative, a negative Q, if you will. Okay, so that would be A. Let's take a look at B, melting of ice. Now, if we have ice and we melt it, it's going to turn into water. Now, is this something that is going to release heat or something that's going to require heat? And my answer is it's going to require heat. So here, this absorbs heat. So that means that this is an endothermic reaction. Or I should say process, it's not a reaction. So this could be an event, if you will. And this is going to be positive Q. So that's B. Let's take a look at C. Raising the temp of water from 25 degrees Celsius to 100 degrees Celsius. So for C, we're going to take a glass of water that's at 25 degrees Celsius, and we're going to raise it to 100 degrees Celsius. And so basically, I think I'm going to need to add fire to it. So here's my Bunsen burner. So I'm going to take heat plus the cold water and turn that into hot water. So heat is absorbed, which makes this endothermic. We're adding heat, and it's a positive Q. Now, D, you're going to take calcium carbonate and turn it into calcium oxide plus CO2, but here you have to add heat to make this happen. So when you add heat, again, heat absorbed, endothermic, and it's a positive Q. And that's how you figure it out. You just have to figure out, was the heat released like a product, or is the heat absorbed like a reactant? And that's the end of this section. Thank you for listening.